tool you may want to create while utilizing TruckDevil is a fuzzer. I have created a fuzzer that is still in development, but I will show you an example of what a script for fuzzing a specific ECU may look like. Fuzzing is a term used to describe a technique for sending a message to a target device or application in order to get it to behave in an unexpected way or to crash. The purpose is to find areas in the code that does not properly validate the input from the user to find paths for exploitation. This fuzzer begins by recording messages for a specified amount of time to determine the baseline. I will begin the fuzzer now, so it can record the baseline in the background while we walk through the rest of the tool. As you can see, it's now baselining. I have it set to baseline for 60 seconds. After it records the baseline, it makes a determination of how many messages each ECU typically sends in a given interval. It also knows which PGNs it normally sends. Then it starts a new thread called anomaly check, which will record messages while fuzzing and then checks on a regular interval whether or not any of the ECUs are behaving strangely or if it has crashed due to the messages being sent during fuzzing. Next is the actual fuzzing. It will send a total number of messages based on the num messages variable that we set. In this case, I set it to 5,000 messages. This fuzzer actually has two techniques for generating the messages that will be sent to the ECU during fuzzing. And I will show the first one, which is mutate. This takes in a J1939 message object and then mutates the various parts of the message depending on the arguments given. It can mutate the message's priority, source and destination addresses, PGN, and data. Probably the most important part here would be the PGN and data portions. For instance, if you want to fuzz a specific ECU using a specific PGN, you would simply run mutate on it to modify the data portion of the message. The next technique that we will look at is generate. This creates a J1939 message from scratch rather than from an existing message. You can specify the various parts of the message that you wish to stay static. For instance, if you want to fuzz the brake controller with the address of hex 0B, you would set the destination address here to hex 0B. As you can see, each part of the message that you wish to generate is done so randomly. There's another argument here called option, which allows you to decide if you want the data portion of the message to be completely random with a random length of bytes, or if you want the data portion to still align with the J1939 standard for the specified PGN. If you select 1 here, it will attempt to create the data portion in line with that PGN's data length and in the format specified by the J1939 standard. 2 will generate the data randomly, but will stick to the data lengths of the specified PGN. 3 will generate it based on a random length and random data. After each of these fields have been generated, it simply creates J1939 message object and returns it. So now, going back to the fuzzing portion, you can see that for each message to send, it will decide whether to mutate a message from the baseline or to generate a message based on the mode you have selected. In this case, I have mode 1 selected, which means I will only be generating messages. I have the destination address set to hex 0B because I'm targeting the brake controller. I have the source address set to 0 because I'd like to pretend to be the engine control module. And here's where you can really tailor your fuzzing to the specific ECU that you're targeting. Once the message is created, it calls the send message function, and then starts the loop over again to create another message and send it. In the background, we still have the anomaly check function running. This function is collecting all the messages and analyzing them. If it detects an anomaly, as in it thinks the ECU has crashed, it will stop the fuzzing and alert you that a message you sent caused an issue. It's unlikely that we'd find it a problem during this demo, so I will just simulate a crash now by powering off the brake ECU so you can see how it reacts once it detects this. It may take up to 20 seconds in this case for it to detect it. As you can see, it has printed out a crash analysis and stopped the fuzzer from executing, as you must manually restart the ECU before you can continue fuzzing. It shows the source address of the node that crashed, and it also shows how many messages it sent per second versus how many it sent in the baseline, as well as a percentage of the difference. It also has a breakdown of how many messages it sent from each PGN. Lastly, it reports that it created 2 log files and stored them in the current directory. These files contain the messages that the fuzzer sent in the previous and current intervals, so you can determine which messages caused the crash. I will open one of these now to show you what that looks like. You can see all of the messages that were generated and sent to the brake controller. Because the crash was only simulated in this case, these messages did not actually cause the brake controller to crash.